Hey everybody, Mrs. Bodechon here. Today we're going to look at 8C, which says I can analyze and interpret data to identify the relationship between mass and gravitational force for falling objects. So your AKS portfolio, you have this image here. It says analyze the data given in the diagram, compare and contrast the mass and the weight. So we're first going to look at that, okay? We have two different pictures here, one of the Earth and a guy, and one of Mars and a guy, okay? And if we compare their numbers, the mass is 50 kilograms on both, but the weight changes. So the weight of the one on Earth is 110 pounds, and the weight on the one on Mars is only 42 pounds, but they're the same guy, all right? So what that can lead us to believe is that our mass, which remember what mass is, you guys, it's kind of how much matter something makes up, right? So it's everything inside. So when we're talking about this guy, we're really talking about like his blood, his bones, his muscle, right? Like everything that's inside of him, the matter that's inside of the person makes up your mass. And your mass doesn't change no matter where you go. If you're on Earth, if you're on Mars, if you're on a moon, if it doesn't matter where you are, your mass is going to stay the same because you're made up of the same matter. Okay. Now, what does change is your weight. And you can see this displayed here. You have a larger weight on Earth and not so big of a weight on Mars. What can we infer about this? Well, Earth is a lot larger than Mars, right? And therefore, Earth's gravitational pull on us is going to be a lot greater. And that is exactly why we weigh more on Earth than Mars. Okay, so gravity is really between two objects. In this case, it's between the guy and the planet, right? Because Earth has such a large mass, it's pulling down on the person so much more. So the gravitational pull is definitely increased. And our weight is just our mass times the gravitational pull on us. So that's why that number is so large on Earth compared to Mars, where Mars has a smaller mass. So when we do the mass times the gravitational pull of Mars isn't very massive. It doesn't have a whole lot of gravity compared to Earth, right? So when we multiply that, our number is going to be pretty small in comparison to what it was on Earth, okay? So the question that is next says, if this person was floating in outer space, what would this person's mass and weight be? Again, the mass would not change. It would be 50 kilograms, but the weight at that point would be almost zero. Because if you're floating in outer space, you're not next to a really large body like a planet, right? Therefore, you don't have anything pulling on you gravitationally wise. You do have other things out there like, oh, the nearest star, the nearest moon, the nearest planet. But because their distance is so far away, you don't have a whole lot of gravitational pull on you. So you're kind of almost weightless. You're almost zero, all right? The next one on your sheet is a graph. And it says analyzing the data from the graph, what relationship can be determined about mass and gravity? So if we're looking at this graph, we can see that we have all of the planets from the solar system, and then we have their gravity for our y-axis. So if we look at this, we can see that as mass increases, gravity also increases. So the bigger planets, and you guys know that like the biggest planet is going to be Jupiter, of course. The larger planets in our solar system are going to be like Uranus and Pluto, and I'm sorry, not Pluto, Uranus, Saturn and Neptune, Pluto being the teeny tiny, it's not even really a planet, it's like a dwarf planet, right? So the smaller ones are going to have less gravity, like Mercury, Mars, and Pluto, okay? So analyzing the graph, what relationship can be determined about gravity and distance? So as distance increases, gravity decreases, and that's this graph right here that I was kind of hiding. So we have gravity is our y and distance is our x, and you can see that they have an inverse relationship, okay? So as we increase distance, we decrease gravity and vice versa. So as we look at two objects, if they get farther and farther apart, we have less gravitational pull. if they get closer and closer together, they have a stronger gravitational attraction to one another, okay? And then the last question, number 3, says, what 2 factors does gravity depend upon then? Well, it's going to be mass and distance, right? But gravity depends on distance. The farther away you are, the less gravity you have, right? The closer you get, the more gravity, and mass. So if an object is more massive, it has more gravity, and if it's less massive, it has less gravity. Moving on, you guys see this on your paper. So it's defining free fall. It says Commander David Scott conducted a free fall demonstration during Apollo 15 moon landing. He dropped a feather and a hammer at the same time on the moon. Both items landed on the surface of the moon at the same time. However, they're dropped at the same time on the Earth. If they were dropped at the same time on the Earth, the hammer would hit the ground faster, right? So this sounds really confusing if you're thinking about it. So what conclusions can be made here about mass, gravity, and the forces of these items on the moon versus on the Earth? So here's a picture of this scenario here. And let me just move. There we go. So if we are on Earth, this is what it would look like. We have the hammer and the feather. We drop them. The hammer is going to hit the ground first. If we are on the moon, right, and this is like our astronaut on the moon, he's dropping it, right? So he drops it from this level. They would both hit at exactly the same time. So here's why. So the mass of the objects do not change from the Earth to the moon. Remember, mass stays the same. Gravity pulls on the objects equally. The distance is air. The difference is air resistance. So there's no air on the moon. So they both drop at the same rate due to gravity. And you can see that here. This one says in a vacuum, right? Like on the moon or in outer space, like a vacuum, where there's no medium, all right? So on Earth, there's air resistance, which slows down the feather a lot and hardly slows down the hammer, making it land first. So you guys have seen a feather drop before. It kind of catches the air, right? And it sways back and forth because the air resistance for a feather is so great. But the air resistance from a hammer is not so great. So is there air resistance for a hammer? Yes, but just not a lot. So it's still going to drop really quickly while the wind or the air is going to catch that feather and it's going to sway down and take a long time to actually drop. So what is terminal velocity? And it's asking us to fill out this parachuter's journey down from jumping out of a plane. So let's go ahead and talk about first, what is terminal velocity? It's the constant speed that a freely falling object eventually reaches when the resistance of the medium through which it is falling prevents further acceleration. And that may sound really confusing. So we're going to step through this parachuter jumping out of the plane, and we're going to fully understand it as we go. Okay, so this guy just jumped out of a plane right here. Okay, just like going, woo, jumped out of the plane. Right here, he is accelerating due to gravity. And you can see that in this arrow or vector, right? Is going downward because he's accelerating due to gravity. He's increasing the speed downward, right? This picture right here, we have a small drag, and drag is air resistance. So we have a tiny arrow, which is representing our small drag, a small increase in acceleration down still. So if we did the net force, our net force would still be in a downward motion, okay? Still falling. Now, this one right here, we have equal arrows. Okay, so this is unique. This is terminal velocity. Terminal velocity is when we balance drag, which is air resistance, and our gravitational force downward. Even though it's balanced forces, we're still falling through the air, of course, right? There's nothing stopping us. We're still falling. But we've now reached our maximum velocity downward. So we are no longer accelerating. We have reached terminal velocity. We can no longer go faster in a falling motion because our forces are equal. They're balanced. What throws that off is when we open up our parachute, right? We open up our parachute, as you can see in this picture, all of a sudden we have this huge drag force, which is slowing us down. In fact, it shoots us up into the air at first, right? Because it's so big. And then it slows us down. The wind catches that parachute, and then we slowly start to fall again. All right, and until we reach terminal velocity again, but this is going to be a new speed because now we have a parachute that's making us go slower, right? So our drag force is going to equal our downward force from acceleration due to gravity. All of it's going to balance, and we're going to reach a new maximum speed moving down with no further acceleration. And that's called our terminal velocity. And that's going to be our final stopping point for when we finally land on Earth. And that pretty much sums up 8C, you guys. If you have any questions, let me know.